So short presentation about this company. They are one of the very large dairy companies in Switzerland. And they do have several sites in the country. The one factory on which the case study has been done is the one in Fribourg, in Villars-sur-Glâne. And these are processes making cheese and butter and milk products, especially dry powder milk also. What you see on the picture to the right here is their facility here, or their factory. Interesting to know that beside gas boilers, they do have the district heating as a heat supplier. And also, as you can see on the roof to the left, the solar collectors are also a heat producer for their factory. So to find potential opportunities for high temperature heat pump integration, there was no complete pinch analysis available on the factory. And so there have to be some guess made on this matter, but there were three main concepts that stood out. The one was to supply steam to the milk pemerate powder drying plant, which is one particular process they have. Another one with little focus like this on a process would be the very large heat pump, which could boost the district heating network distribution temperatures. And this is what is here shown in the picture below. At present, they supply at 105 degrees, but were they to lower this temperature, and this is unsure, they could be an really interesting opportunity to install a large capacity heat pump to boost this temperature. And last, of course, would be large-scale heat recovery across the factory to feed a hot water loop. And this could be also increasing temperature by a heat pump. This is actually under study present. So the selected case study was to focus on this specific milk pemerate powder drying process. The reason for this being that the pressure of the steam needed is quite low, which is favorable for a heat pump. The lower the temperature or the pressure, the best the coefficient of performance. It does use a fair part of the steam consumption from the site. And although it is a semi-continuous process, looking at all the streams in like that make up this process, that would offer the simultaneity and also proximity between the sources and sinks. Proximity is a matter here. The factory is built in a high tower, which has 9 stories, so it adds some complexity to it. And so there was a measurement campaign that has been led in order to assess which were the fundamental needs of these process streams, the heating and the cooling, versus how these are currently supplied. If there is 3 bar steam used in the equipment, is this really what it needs, or can we optimize this somehow? And the heat sinks that have been included in the study is the steam to supply the paddle dryer, and this is 1.8 bar steam that is needed for it. Hot air heated for as sweep air for this dryer, as well as static and fluidized bed equipments. And the source is, of course, this exhaust air coming out of the equipment around 66 degrees, as well as a hot water loop, which supplies heat around the factory. Now, this one wasn't taken into account right away because it is supplied by the district heating network, and we'd rather use waste heat from the process. So the analysis led to the following curves here. To the left, the composite curves, first of all, show this heat recovery potential, which is the zone in the middle called HR, that heat can supply through heat exchanger from the hot to the cold streams without the need of any further heat pump equipment. So always to be made first. And then by integration or calculation of the grand composite curve, which is the curve in the middle, so all internal heat recovery is already integrated, and what is left here from the pinch point, which is situated at around 70 degrees here, the curve going down shows the available heat at each temperature level and the thermal load linked to this, whereas above the pinch temperature, this is the heat need that needs to be supplied. So the pinch analysis showed this as a potential solution with an evaporator at around 38 degrees, condensation at 120, and this would lead to a COP rather low of 2.3. Now, the constraints that we found versus these conclusions or proposition is that waste heat or streams are already used and valorized in a heat recovery loop, also to exchange between together. So this is already realized. And also there is very, very little space available in the heating room for any heavy modification to the air heating systems in place. So this led to the following integration concept that was kept and studied in this case study. So the steam supply to the paddle dryer is the objective of the project. And as all the potential heat recoveries are already valorized, the hot water loop has been used as a source for this heat pump integration project. Another concept that had been inquired was to supply higher pressure, 4-bar pressure steam for the paddle dryer, as well as all the air heaters, in order to see what this would lead to. And that proved to be a technical no-go regarding the low stream or the low capacity and the pressure needed. So besides the only focus on the heat pump machine itself, there is various points to be checked in such a project. The first being the simultaneity between the sinks and source, of course. In this case, as the heat is provided by the hot water loop around the factory, it is available at all times, and this is a great advantage. Heat storage, hence, is not needed in this case study. Space is available right beside the paddle dryer, so there is an opportunity to place the heat pump right there, although this is located at the 5th floor in the factory. Next points all have been checked, and the project has been evaluated as feasible. So as a preliminary evaluation with the first hypothesis we had, so producing 1.8 bar steam for around 500 kilowatt capacity is what we are looking at. The MVR heat pump is what has been, is what has been selected as a technology, and it could have, regarding the information you can see on the right on the manufacturer data. With a lift around 20 degrees, we are looking at almost 10 or even more. We took a COP of 9 for this first evaluation. The operating time is 2,700 hours a year, quite modest, but this is how it works for now. And so hypotheses were made, which led to the estimates of 15% annual energy saving for this steam production, 94% lowering CO2 emissions, and a payback of 4 years, including subsidies that are available for industrial heat pumps in industry. So I said MVR technology is what has been selected, and this is mainly because it was a requirement by Cremo of not wanting any refrigerant fluid in a heat pump that would be set up amongst the production processes. However, MVR technology is also a very well-established technology with good efficiencies, and it should prove a good solution. At the condition that we are talking about, in order to vaporize the condensate return, we need to work at subatmospheric conditions, but this works. And the small capacity of the heat pump we are looking at proved to be a real challenge, because it is out of the capacity range of the products on the market mostly. And the other point was, how are we going to bring up this machine up to where we want it to sit? And there was a solution to set up this on 2 skids that make it possible to be flexible, to get into the place and assemble as needed. So we found that this was a technically feasible options with an available machine on the market. This is what the integration scheme looks like. On the right, you can see the paddle dryer with the 5 different steam injections at various very low pressure condition. In the middle, within this red dotted border, is the heat pump that EPCON has proposed for these conditions. It is taking its heat source to the left, that's coming from the hot water loop. And there is a small makeup needed also to be used as a de-superheating within in between the compression stages of the machine. And then the steam that is produced is then injected into the paddle dryer, integrated with the existing steam supply that would be kept as a backup system. Now, one point here is that the COP of that machine shows to be around 5.4, which is quite far from what we had expected. Now, why this performance gap? What we are facing here is merely a technical issue of compressor technologies, and this is really linked to what's it called, the domain of operation of different compressors. As you can see in the graph at the bottom here, the centrifugal compressors have very good efficiency, but they work for increased stream flow rates. So this is what explains the gap with the efficiency that we were expecting. And as a general matter, the efficiency of the compressors was always be rising with the larger equipments. So down to the project results. After costing that complete integration solution, we found a 1.5 million Swiss francs capital or cost, and the specific cost would be more than 3,000 Swiss francs per kilowatt installed, which is extremely high. What we can see, on the other hand, is in the blue table to the right, the breakdown shows that the integration costs globally are very modest, and this is also due to the fact that the heat pump is installed quite simply and very close to the delivery point where the heat is supplied. So there was no profitability on this. So what has been found is that the capex overcost for these projects is around 72 Swiss francs per ton of avoided CO2 emissions, and this is clear. Changing from business as usual to decarbonized steam production does have a cost. Now, I guess each factory, each company has their own view on their targets and what they are ready to invest also for this transition. Now, the most important reasons for this non-profitability here are really that the heat source is taken from the heat water loop supplied by district heating. So this proved a solution for this limited process or boundary around the process that we set for this case study. However, by opening this to a broader look at alternative heat recoveries could help in this matter. The heat pump has a very high specific cost, and this is always the case for small equipment. The bigger the better, for that matter. And this coefficient of performance has really been much lower than expected. So all this, with the limited operating time over the year, made it maybe not the most cost-efficient project. And the subsidies is another point. Given the eligibility constraints, at least one of the two is for sure not obtainable, and the Swiss Energy program is still to be confirmed. This would be or not a possibility. However, the environmental benefits that come out of this project are really like impactful, and the annual CO2 emission reduction close to 100% is a very good result on its own. So improvements of this cost efficiency, I've mentioned fine waste heat. If that waste heat has to be cooled further with utilities, then this utility cost is going to play in the favor of the project. Larger heat pump for efficiency and lower costs, operating time, and then the cost of the resource of the gas with the variation could make it an impact on that economic performance as well. I mentioned here two subsidy programs that are available for heat production by use of heat pumps for the industrial heat. The first one gives an amount of money for capex reduction, really, whereas the second is paid off as an annual amount, which will help on the OPEX aspects. Now, the eligibility conditions are always to be checked, in particular looking at companies which have tax refund, CO2 tax refund, target agreements with measures on heat production modification or replacement. This is not always possible to get. So coming shortly to the conclusions, well, there is a feasibility that has been proven for this case study. And integrating a heat pump instead of a fossil fuel heat production or even steam production is always a good idea on environmental grounds and CO2 emission reductions, even if the machine contains refrigerant fluids, but it's not even the case here. So very large annual CO2 emission reductions of 98%, which is really interesting. The installation at process level have proved possible in this case. Sometimes installing the heat pump at a utility level in a heating room can prove easier, but each has to be assessed. Larger heat pumps supplying an existing heat network can be a great option, although it would also be supplying higher in the temperature or pressure levels as for one specific need. So always produce and try to supply the heat as close as possible to the fundamental heating needs of each equipment is really a key message here. And then the challenges faced have been really this profitability, but we also all know that the technologies needed to decarbonize do have a cost, and this is part of the game, I was going to say. So low steam flow rates have really proved unfavorable for MVR fans. In particular, it would be the case for various technologies, but I think it's really detrimental to this MVR. And then really the data would be a key point also. Having a very well-known in processes, streams, the needs is really key to finding the best matches also between sinks and sources, the best way to integrate it. And I think that's it for me now. I added a link here for those of you who'd like further information, and the Annex 58 on high temperature heat pumps has been providing reports on all sides of this topic, really, which are very interesting to go have a look at for those of you who are interested. So thank you very much for your attention.